Hey everyone, this video lecture will concern the Doppler effect, which is the last subject of chapter 17. And I think there's one problem involving it, and I'm going to do an example that's somewhat similar to that problem. But first, let me share my screen and describe what the Doppler effect is. Um, and I'm sure you've all actually experienced the Doppler effect. So let's go back to the beginning here. Basically, what the Doppler effect is a change in the frequency of a sound depending on the relative motion between the source of the sound and the observer of the sound, or the receiver of the sound wave. And generally speaking, what will happen is if the objects, the source and the receiver, are moving closer together, the frequency will be shifted upward. That is, the frequency that the observer hears will be higher. If the relative motion is moving away, that frequency shift will be downward or negative, and you'll hear a lower frequency. So there are two kind of isolated situations that can happen. The first one is the source is moving, but the receiver is stationary. So let's assume in this situation that the source, which is the car here, is going to move toward the observer. And the observer could be either behind the car or in front of the car. Now, the first question is, I said that you'll hear a higher frequency if you're in front of the car because the car source of sound is moving toward you, and a lower one behind. The basic reason for this is that, as you can see, in front of the car, since the car is moving toward the wave that it just emitted, the wave does not get as far away from the car before the next one is emitted. That is, the wavelength gets shorter. And as you know from our basic wave equation, wave speed equals frequency times wavelength. If the wavelength goes down, the frequency has to go up. So this observer B, who is not moving at this point, would hear an upward shift in frequency. They would observe a higher frequency. Whereas behind the car, the wavelength is going to get longer compared to if the car is just stationary. And observer A behind the car will actually hear a lower frequency. So if you're standing on the side of the road, let's say, and you have maybe an ambulance is coming toward you and then it passes you and moves away, what you will hear is a high frequency coming toward you and then a lower one as it goes away. You can also see this sometimes with a plane, for example, flying overhead. So now let's go to the opposite situation where well, actually, I guess I should do the equations first. So if the source is moving and the receiver or observer is stationary, the wavelength is shortened. And if the source is moving toward the lengthened, it's moving away by an amount. So the point is it's either shortened or lengthened if you're in front of or behind the car. But the thing is, we're going to say the frequency of the source is Fs, frequency of observer is Fo, and then the speed of source is Vs. The V with no subscript is the speed of sound, and VO is the speed of the observer, which in this particular situation is 0. The wavelength that the observer hears is shortened from the source wavelength by this amount, the speed of the source times the period of the wave, right? Just distance equals velocity times time. So I've got a minus or plus. It's shortened if you're moving toward, or if the source is moving toward the observer, and plus it's lengthened if it's moving away. Just using that the frequency is 1 over the period and doing some manipulation after some algebra, we get this equation. Frequency of the observer is the speed of sound over the speed of sound minus or plus the speed of the source times the source frequency. Now, when do you use the minus sign? Well, when you are moving toward, when the source is moving toward the observer, because that's going to shift the frequency up, right? And then minus sign in the bottom, we need that to make the denominator smaller, so the frequency does go up. You'd use the plus sign when you're moving away, or when the source is moving away from the observer. Okay, so now we need to go to the next situation, which is if the source is stationary and the receiver is moving. In this case, it's a little bit different reason for the Doppler shift. The wavelength isn't changing in this case because the source is not moving, it's stationary. But as the observer moves toward the source, for example, the wave seems to come faster. It seems to be approaching you faster as you move toward the source. And conversely, if you're moving away from the source, it's going to move slower. So it's really the speed of the wave that changes depending on your motion. And so now we have speed of the source is 0, and the observer is now affecting the speed. So ultimately, the equation you get is this one. Frequency of the observer is the speed of the sound plus or minus the speed of the observer over the speed of sound times the frequency of the source. So again, you're going to use the plus sign here when the observer is moving toward the source, because that would give a higher frequency. And you're going to use the minus sign when you're moving away, because that would lead to a lower frequency. So I'm not going to go through that derivation. I'll put it here at the end. But just to summarize, this is the situation. If the receiver is moving and the source is stationary, the wave speed is increased if the receiver is moving toward and decreased if moving away. Now, I didn't put the amount, I just put the Doppler shift equation, right? So it's going to be sped up or slowed down, and I will put those equations later. The main thing I wanted to point out is the actual equations we have here. Now, the next case would be, well, what if both are moving at the same time? So there is nothing that's zero velocity, right? The observer and the source are both moving. We just kind of combine the previous results. So this is our general Doppler shift equation. The frequency of the observer is v plus or minus the observer speed over v minus or plus the source speed times the source frequency. And I'm going to do an example which hopefully will help you again remember which sign to use here. But it's going to depend on whether you're moving toward or away, right? And observer and source have different impacts on that, because one is in the numerator and one is in the denominator. Now, before I do the example, I want to kind of point out an extreme case here. What if the source were moving so fast that it's moving faster than the speed of the wave itself? Faster than the sound speed. Right. So in this case, you might have a jet that is going supersonic. It's faster than the speed of sound. Now, before it hits the speed of, before it is going too fast, before it's subsonic, it's not going faster than the speed of sound, you get the compression of the wavelength in front, right? So that would increase the frequency that someone in front of the plane would hear. Once you get to the to the speed of sound, you're at what's called Mach 1. Now all the waves are overlapping, and you're going to get some constructive interference going on there. It's going to create a very intense sound. And so this is really the source of what we describe as a sonic boom. If a jet flies overhead, you might hear a very loud sound. Now, if you go faster than the speed of sound, you'll get sort of a cone, a shock cone, or a shock wave cone. So that, let's say I'm standing on the ground down here below the wave. Well, the plane's actually going to be over here before I hear the sound, but I get a loud constructive wave, intensity here along this cone. So once that cone passes me, I'm going to hear that loud sound, that large amplitude sound wave. Another example that's not related to sound waves that you've probably seen is, let's say a boat is on the water and it travels faster than the speed of the waves on the water. You'll get what's called a bow wave, a big wave in front of the boat, which is like the shock wave that we get up in front of the plane. And you'll get a wake. Now the wake is like the shock cone on the water. So if you're floating on the water, right, as that wake passes you, you'll bob up and down a lot, because it's exactly the same thing. You're getting a large amplitude due to that wake having constructive interference along that shock cone. All right, so that's the idea of shock wave. So let's do an example. We're going to do an example using a bat here. And in this case, we're going to have two Doppler shifts, because the question is, you've got a bat flying towards a wall, and it's going to receive a reflected wave from the wall. The ultimate question is, what is the frequency of that reflected wave? So we're going to assume that the sound emission frequency of the bat is 39,000 hertz. And during one fast swoop directly toward the flat wall surface, the bat is moving at 0.025 times the speed of sound. What frequency does the bat hear reflected off the wall? We've got to do this in 2 steps, but let's first of all write down our known values here. And first of all, we know the frequency, in this case, we know that the frequency of the source is 39,000 hertz. We also know that the observer, which in this case is the wall, right, is not moving, so it's 0. The speed of the source is 0.025. Now, times the v, which is the speed of the sound. Now, we could calculate that if we knew the speed of sound exactly. Maybe it's 343 meters per second, but it'll turn out we don't need that. We can just use this. So what I want to get is the Doppler shift at the wall. This is a case of the observer not moving, but we can use our general equation, which I'm going to put up here. So V plus or minus VO over V minus or plus VS times FS. And so the idea now is that my VO is 0. So the observed frequency is going to be V plus or minus 0, right? So there's no VO speed, and then V minus or plus VS, which is 0.025 V. The question is now, which speed are we going to, or which sign are we going to use? Well, it doesn't matter for the top, but for the bottom, we know that the bat is moving toward the wall, and we need a higher frequency. We're going to use the minus sign. So we're going to get V over V minus 0.025 V, right, times the 39,000 hertz. Now, I don't need to plug in the speed of sound because the V's will cancel. And if you do this, you'll end up about with a 40,000 hertz frequency. So this is the speed, or sorry, the frequency received by the wall, but there's a second part. The wall will now reflect the wave back to the bat. So after reflection, what we want is the frequency heard by the bat. So now the source frequency is that reflected off the wall. It's the 40,000 hertz. And our source frequency is 0 because it's now become the wall. So upon the reflection, it's as if the wall acts like a new source of sound with the new frequency. And so our observer speed is the 0.025 V. And we're looking for an observer frequency that is what the bat is going to hear. So now we're going to go back to our equation. I'm going to go through it a little more quickly. We do have an observer speed, and we're moving toward the wall. The observer is moving toward the source of sound. So I'm going to use the plus sign. Vs is 0. And I have Fs. So plugging in the numbers, I'm going to get V plus 1.025 V over V, now times the 40,000 hertz. V's will all cancel again, and if you do this, you'll get about 41,000 hertz. And this is the ultimate answer we wanted because that is the reflected frequency that the bat will actually hear. Okay, so hopefully that example makes sense. There are some problems in the book that do this as well as just one or the other. The trick really is usually getting used to these signs. The last 2 slides here, I am just going to put up kind of a summary of all the derivations. So I'm not going to go through this. It kind of summarizes what I just talked about and specifically writes out the formulas. But the last slide, I just want to summarize the combined equation, right? We are combining the two source stationary, observer stationary situations into this equation. Now, sometimes you'll see F prime instead of FO. Here it's F0 instead of FS. So again, be aware that certain people will write the equations differently, but I'm going to use the top sign if the motion is toward, so the plus or the minus, and the bottom sign if the motion is away. And notice, there can be sometimes you'd be moving at an angle, and we would have to modify the equation for that.